Okay, so we're going to talk more about compact sets today. So this is the main, the kind of the big idea, one of the big ideas. So you remember what we finished up last time was that what was it? Yeah, every compact set was closed, right? And we had that kind of interesting proof where you took you took points in the complement, and then you took a point in the complement, and then you took balls around every point on the set, and you covered the set, and you took a finite subcollection of that, and then intersected everything, and then that gave you and that showed that the point was interior to the complement, right? So that the complement was open, right? Okay. So we're going to continue on with more properties, heading towards the great theorem of Heine-Borel, which characterizes compact sets in Euclidean space. So okay, let's get going. So first thing we're going to show is the following: that whenever you have a let's see, so you have a compact set sitting inside of X, right? I always use K for compact. I've sometimes seen this notation to say K is compact in X. Okay, I've never used this, but I've seen it occasionally. So you have K, this is a compact set in X, and then you have F that's sitting inside of K. Okay, so if K is compact and F closed, then in fact F is also compact. Okay. So that's the theorem, that whenever you have a closed subset of a compact set, so in my picture, compact sets are always rectangles. You have a closed set sitting inside of a compact set, sitting inside of some metric space, right? Anything like that is always going to be compact. Okay, and the proof is, so of course you want to show that this is compact. So you want to show that given any open cover G alpha of F, there exists a finite cover. There exists a finite subcover. Right. That's the goal. Right. No matter what cover you have of F, you can always make a finite subcover of it. So, right, got some sort of infinite cover here. And you want to show that you always have some sort of finite subcover. Okay. Anybody know the idea of this one? Anybody remember from reading the idea of this one? So what we're going to use is that K, the thing containing F, is compact, right? So F we don't know about, but K certainly is compact. Okay, and so the idea is to take this cover and then extend it to a cover of K. Okay, and we'll extend it to a cover of K by adding in F complement. Okay, F complement, we've covered F already. Then we throw in F complement, that covers everything else, right? So throw in F complement, right? So the proof is consider this open set union F complement. Okay, so throw in F complement. Okay, right? That's an open cover. Okay, right, because it covers the whole space now. In fact, right, it covers all of X. Right, we covered F and we covered everything outside of F. Okay, so it's certainly an open cover, of X, let alone K, of all of X. Okay, so it's an open cover of K, so that tells you that there's a finite subcover, right? K compact implies that there exists some finite subcover. Right? Maybe like, you know, G1, oops, G1, G2, Gn, and maybe F complement, right? Possible. Okay. Okay, so there exists some finite subcover. So that's a finite subcover of K, right? That's a finite subcover of K. But then, if we throw out F complement, right? So this covers all of K, right? Certainly it covers F, right? Note that this covers F for sure because it covers K, right? So, so are we done? Do we have our finite subcover? We're not quite done, right? Because we wanted a finite subcover of this, right? Right now we've got a finite subcover of this, right? But throw this out. We just throw this guy out because we don't need it, right? We're trying to cover F, right? G1, G2, through Gn still covers F. Right? We don't need F complement to cover F, right? So toss out F complement, and then we get, you know, a bunch of G's that cover F. Well, that's what we were looking for. We were looking for a bunch of G's, you know, G alphas that covered F, and we've got a finite number of them that do so. Okay, so of the G alpha covering F, which is what we wanted. Does it make sense? Yeah, question.
Is the reason that F needs to be closed so that F complement is open?
Exactly.
And it can be in the open cover?
Exactly,
Okay.
exactly. If it were not, then this wouldn't be an open cover anymore. Okay, exactly. Okay. Any questions? So, right, so the idea is, right, we start off with an open, we're trying to show this guy is compact. We start off with an open cover of it, the G alphas, right? We throw in GF complement to get an open cover of K. K being compact means that we can take finitely many of them, right? So there's going to be only finitely many of these guys that, you know, maybe plus F complement cover all of K. Toss out F complement if it's in there. Toss out F complement if it's in there, and we're left with a bunch of G's that still covers F. Right? And that's it. Okay. 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 The next one is a little bit sort of more complicated than, the next property is a little bit more complicated than that. So it goes like this. So suppose you have, so again, as usual, you have a metric space. And you have an infinite number of compact sets. You have a collection of compact sets. Okay. If they have a certain property, then the infinite intersection is non-empty. Okay. So this is saying that you know, there's no guarantee that you know, when you intersect an infinite number of sets, it's going to be non-empty. But if they're compact sets, so let me say it this way. So So here's the property. If the intersection of any finite subcollection is non-empty, any finite subcollection of the K alpha is non-empty, then the intersection of all of them must also still be non-empty. Okay. So I call this thing like the finite intersection property. I think that may be what they say in the book. Anyway, if they don't, this is what I call it, the finite intersection property. Okay. So you've got this collection of sets with the property that whenever you intersect finitely many of them, the intersection is non-empty. Okay. Then if they're compact, right? If they're compact, then the infinite intersection is also non-empty. Okay. The compactness is crucial. If we had just open sets, even if you have the finite intersection property, that doesn't guarantee that the infinite intersection will be non-empty. So for example, if I have a bunch of open intervals, right? If I have a bunch of open intervals, say, like from 0 to 1 over n, say, right? Well, as for n ranging over the natural numbers. If I take any finite subcollection of these, well, the intersection is non-empty, right? If I take any finite subcollection, the intersection is non-empty. But when I intersect all of them, I have nothing. Right? There's nothing in here when you intersect all of them. Right? Is that clear? Right? If I have if I take some finite subcollection, suppose I take the 1 through 1/2, through 1/3, through 1/4. I take some finite subcollection. Well, the intersection is just going to be the smallest one, right? Will be the smallest interval, right? And it'll be non-empty, right? But when you intersect all of them, well, there's no point that is, there's no point that will lie in the intersection of all of them. Okay. So you see that, satisfying the finite intersection property doesn't guarantee that your infinite intersection is non-empty. But if you're compact, it does. Okay. So the proof of it is by contradiction. Suppose that the intersection is empty. Suppose when you intersection, you get empty. You're empty. Well, in that case, the complement is the whole space. Oops. Is the whole space. Right? But the complement of the intersection is the union of the complements by De Morgan's rule. Right? By De Morgan's rules, this is true. Okay. So, and then you see that, well, each of the compact sets was closed by the theorem we did 2 theorems ago. So the complements are all open, right? So we have a union of open sets that is the whole space. In other words, we have an open cover. Oops. Of all of x. Okay. Okay. So now choose any of the k sub a's. Right. So choose one of the sets. Let's call it a sub alpha. I'm saying alpha sub 0. Okay. Then this thing is an open cover of that. And so what am I going to do? I have a compact set, I have an open cover, I'm going to take a finite subcover, of course. Too obvious, right? So we know that Ka sub naught is contained in some Ka1 complement union K alpha n complement, right? There's got to be some finite subcover that covers K alpha naught, right? Okay, so did I miss something over? Oh yeah, right. So, right. So of course, K alpha naught intersect the complement of that is empty, right? Because it's contained inside that union. So when you intersect it with the complement of that union, then you get nothing, right? Right? I'm contained inside the set, so me intersect the complement of that set is empty. Right? Okay, now we use De Morgan's laws again. The complement of the union is the intersection of the complements, right? So I'm going to get the intersection of the complements, but two complements just cancel each other out, right? And so I get that this is empty, right? But that tells me that I've got a finite number of sets. I've got a finite number of sets whose intersection is empty, and that contradicts the finite intersection property, right? At the beginning, we assumed that no matter what finite collection you chose, the intersection was always non-empty. Now I've created a set, a finite collection whose intersection is empty, so that's not possible. Okay, so right, if it were possible, if it turned out that the infinite intersection was empty, then what would happen is that some finite intersection would also be empty. But that contradicts the assumption that any finite intersection, and the intersection of any finite subcollection has to be non-empty. Okay. Is that all right? You guys look good? Okay. Okay. Anybody have a question? Anybody have a question? Yes.
So the contradiction led us to see that
This couldn't happen.
that couldn't happen.
Right.
Okay.
Right. We're trying to show that the infinite intersection must be non-empty. Okay. Right. And we say, suppose the infinite intersection is empty. That leads to a contradiction with the hypothesis.
Okay.
Okay. Okay. Right. Right. Yeah. Right. So you notice that if we had done this thing using closed sets, that whenever you took the infinite intersection, you'd still have the point 0. Right. You'd have the point 0. And that's the thing, that whenever you've got compact sets whose finite intersections are non-empty, then the infinite intersection is guaranteed to have a point in it. Okay, so right, we say, well, suppose the infinite intersection doesn't have any point. Well, that would force somewhere along the line some finite collection to be empty. Or the intersecting of some finite subcollection to be empty. Okay. And this is going to be crucial in the proof of Heine-Borel. So, Now, just now, you said I was basically using the fact that these sets were compact. We haven't proven that yet, that a closed and bounded interval is compact. But that's what Heine-Borel is going to tell us, that closed and bounded intervals in Rn are compact. So we don't know that yet. We actually don't know that yet. Okay. So, okay. So the next theorem I'm going to prove is sort of like showing that intervals have the property that I just proved for compact sets. So we just showed that if you have compact sets, then finite intersection property implies infinite intersection is non-empty. Okay. So if we knew that that closed and bounded intervals were compact, I wouldn't need to prove this theorem. Okay. But I'm going to prove it. Basically, I'm going to prove this fact. I'm going to prove something like the previous theorem for closed and bounded intervals. Okay. So the theorem goes like this. Suppose you have actually, before I do it, sorry, I should do something else first. Okay, sorry. Okay, so sorry, before I do that, let me do this other theorem, which is, again, part of Heine-Borel. So suppose you have K a compact set, and E a subset of K. If E is infinite, then there must be a limit point in K. Okay. E has a limit point inside of K. Okay. This property that any infinite subset will have a limit point in the set is called limit point compactness. K is limit point compact. So in other words, any infinite subset of K has a limit point in K. Okay, so what we're showing here is that K compact implies K limit point compact. K compact implies K limit point compact. Okay. So historically, actually, this idea of limit point compactness was like the dominant idea of compactness initially. Like people thought that this was the right way to think about compactness, and what we now call compactness was called something else. I forget what it was called. But then eventually people realized that this was actually the right way to think about it, like sort of like the easier way to think about it. And so this thing became it lost its secondary name and became compactness. And then limit point compactness got other names like Bolzano wire stress compactness or something. Wire stress being wire stress. I mentioned wire stress, yes. Yes. The greatest mathematician of the late 19th century. I've never said this? No. Okay, sorry. No, it's kind of like an embarrassing story for me, but yeah. I was at a party of mathematicians when I first went to Indiana University, like a sort of welcoming party actually for the new hires, and I was talking with one of the mathematicians, and he said to me, "So, who is the greatest analyst of the late 19th century?" And I was like, I didn't want to make a mistake. And inside I was thinking, wire stress? It's probably wire stress. but he's like, come on, tell me the answer. Who is the greatest mathematician of the 19th century? And the greatest analyst of the 19th century? I was like, I don't know. I just didn't want to say anything. And he's like, and then he just like shouted across the room to somebody like, hey, this guy doesn't know who the greatest mathematician of the greatest analyst of the 19th century is. And he's like, and he said to me, it's Weierstrass. Okay, fine. Anyway, so yeah, that's my bad experience with Weierstrass. But I really admire Weierstrass when I was learning mathematics. Weierstrass is, a great mathematician. Just wasn't clear he was the greatest mathematician. Okay, anyway, yeah, that Weierstrass. Okay, so we're trying to show that K compact implies that K is limit point compact, right? That whenever you've got an infinite subset, it's guaranteed to have a limit point inside the set. So notice that, like, if I have an open set, I can create an infinite subset. Suppose I look like this, right? And I look at things of the form 1 over n, as I always seem to do, right? If you look at the set of points 1 over n, right, n from 1 to infinity, right, 1/2, 1/3, 1/4, etc. They don't have a limit point inside this set. Their limit point is 0, right? But that lies outside. Okay, so this open interval is not limit point compact, right? It's not limit point compact because you can create infinite subsets that don't have a limit point inside the set. Okay, so this is a non-example, right? It's not limit point compact, right? Whereas if we were dealing with the closed interval, no matter what you do, you take an infinite subset, you're guaranteed to have a limit point inside there, right? You take some infinite subset, there's going to be some sort of bunching up that occurs, right? There'll be some sort of bunching up that occurs, and within that infinite bunching, the limit point will be. Okay. So anyway, let's prove that. Let's prove that. This is not a proof. Okay, this is just some idea. Okay. This is rigorous. Okay. So again, we'll just do it by contradiction. By contradiction, suppose there is no limit point. E has no limit point. Suppose E has no limit point in K. Okay. Okay, right. So then, for each point Q in K, we know, for each point Q in for each point Q in K, right, they're all non-limit points, right? So we know that there exists a neighborhood. There exists a neighborhood, a punctured neighborhood, such that if you intersect it with E, you get nothing. Right? There's a punctured neighborhood that when you intersect E, you get nothing. Okay. So at most, NRQ intersect E has one element of E. Right? Has one element of E. Right? Maybe the center point, right? The punctured neighborhood intersect E is empty. Maybe the center is in E. If that is, then it has one element. Okay. So then, cover K with the NRQs. cover K with the full-blown elements, full-blown neighborhoods. Okay. There is no plane, no finite subcollection of the NRQs can cover K. Why? Why not? How come we can't have some finite subcollection of these guys that still cover all of K?
Would that mean that one of the neighborhoods contained an element of E, which would contradict?
Well, it's okay for these guys to contain elements of E, right? So like the each of these so we're covering all of K with these punctured neighborhoods. Okay. The punctured neighborhoods don't intersect E. That's true. But the centers might include elements of E. That's fine. But each of these things contains at most, right? Oops, I already said it. Each of these things contains at most one element of E, namely the center. Okay. So now we cover the set with these guys, and then we say, well, suppose there is a finite subcollection that covers K. Okay. Well, then how many points of E? Like suppose there's suppose NRQ1 through NRQN covers K. If that covers K, well then, at most, each of these things contains one element of E. So that would mean that E is finite, right? But we knew that E was infinite. That's the problem, okay. Right, so no finite subcollection can cover K, because if it did, that would mean that E is finite, right? Then the size of E is smaller than N, right? But E is infinite. So yeah, so this is nice, right? So it says that whenever you have a compact set, and you have an infinite subset, then they must sort of like bunch up at some point, right? Inside of K, there must be some point K that, you know, no matter what neighborhood you take of it, there's infinitely many points of E there. They must accumulate at some point. Okay, now let me do this, the thing that I said I was going to do before, that that closed and bounded intervals have this basically like a finite intersection property. So we're in R1 now. And suppose we have I sub n R is a collection of nested closed and bounded intervals. Okay, so in other words, we have I1, we have I2 sitting inside it, we have I3, and so on and so forth. So they're nested. Okay. Okay. So we have some I1, we have some I2, we have I3, and so on and so forth. Okay. So suppose you have a collection of nested closed and bounded intervals, then the infinite intersection is nonempty. Okay. So if we knew these guys were compact, we'd be done. We could just use the previous theorem, right? We'd say, look, they're nested, so any finite intersection is going to result in the smallest one, right? So they would satisfy the finite intersection. They clearly satisfy the finite intersection property, right? And if we knew that they were compact, we don't yet. If we knew that they were compact, we would just invoke the theorem from 2 theorems ago, and we know that the intersection is non-empty. Okay, so we don't know that they're compact, but what we're showing is that they have sort of qualities that are similar to compact sets. Okay, and we're actually going to use this to show that that they are compact. Okay. Okay, you guys all right? Should I open the door? Should I leave the class a little bit? I'll go outside. I'll be back in a minute. Okay, not back. Okay, so okay, yeah. Okay, so the thing to notice is that here's the thing to notice, that you have this sort of relation. So whenever you have one of these compact sets, and you go farther down the line, right? Then this point is going to be greater than or equal to that point, right? And this point is going to be less than or equal to that point, right? Okay. So consider the set of all left points. Okay. Consider the set of all left endpoints. Okay. Any BI, any of the right endpoints is an upper bound. Of that set, right? Because you're never going to go beyond, right? If one of the A's were bigger than that, you wouldn't be nested. Okay, so but because of the nested quality, you know that any of these right endpoints is an upper bound of the set of left endpoints. So now we can use the least upper bound property. That implies that the supremum of E, let's call it, that's denoted by X, exists. Right? So there is some supremum. Okay. Okay. Now it is the least upper bound. It's the least upper bound of the A sub i's. So we know that X is bigger than or equal to any A sub I, right? Because it's the least upper bound of the guys, right? But we also know that all the B's are upper bounds, and this is the least upper bound, right? So we know that X is less than or equal to any B sub I. Okay. So what did that tell you? That tells you that X lies in the intersection, right? Right, so X lies in every interval A sub I, B sub I, which means that X lies in the intersection of all the intervals. So it's just the least upper bound property that gives this to us. Kaylin, are you okay? Yeah? Okay, Okay. Sort of a corollary. The fact is also true for K-cells. So if you have nested K-cells, then their infinite intersection will be non-empty. You remember what K-cells are? They're basically just rectangles, right? So all this is saying, they're products of intervals, right? So this is saying that if you've got nested K-cells, then you can do a similar proof and get that the infinite intersection is non-empty. Okay. I wonder if we can do this. So now we're at a pretty cool point. Let's see if we can do it. 7 minutes. Okay. So here's the theorem. K-cells are compact. Okay. So you start off with a K-cell. So let I be some K-cell. Okay. So basically, it's a product of intervals, AI, BI. So in your picture, you've got one interval, got another interval, right? Take the product of them, right? Take the product of these closed intervals, you get this K-cell in many dimensions. Okay. Let delta denote the length of the diagonal. So that's going to be summation bi minus ai squared, everything summed to the 1/2. Okay, that's just the length of the diagonal using the Pythagorean theorem. Okay. Now, again, we're going to do a proof by contradiction. Suppose I is not compact. Okay. So by not compact means that there's a bad cover, right? i.e., there exists a cover, G sub k, G alpha, of I, for which there is no finite subcover. There is no there's this cover, it's so bad that you never have any finite subcover. Okay, so what you do now is you take I and you divide it dyadically. That is, you split every interval into halves. Okay. Okay. And if we were in more dimensions, then it would be 2 to the k piece, 2 to the k parts. Right? I'm drawing it in 2 dimensions, so we get 2 to the 2. But if we were in k, we would get 2 to the k sub k cells. Okay. Okay. In any case, just it's fine to think of it in 2 dimensions. So then we know that So dyadically divide I into 2 to the k subcells. We know that one of these guys cannot be. There is no finite subcover of one of those guys, right? How should I write? At least one of these subcells cannot be covered be covered by a finite subcover of the G alpha. Right? Because if everyone were finite, could be covered with a finite subcover, that would give us a finite subcover of the original. Right? We said that this thing has no finite subcover of I, right? So there's got to be at least one of these guys that it cannot you don't have a finite subcover of. Okay. Okay. So take that guy, call that subcell I sub I. Okay. I sub 1. Okay. We'll call that guy I sub 1. And then we take, let's suppose it's this one. Okay. Then we take that one and we divide it diagonally, and we say, well, each of these guys also, if we look at all of its subcells, they must be one bad one that cannot have a finite subcover. Because if they all had finite subcovers, then I sub 1 would have had a finite subcover, right? So we call that guy I sub 2, right? We subdivide that guy, and we continue on, so on and so forth. Okay. Okay. So continuing in this way. We obtain a sequence of K-cells, of nested K-cells. I sub n, where right, each cannot be covered by a finite subcover. 2, and 2, the diameter of I sub n is equals 2 to the minus n times the original diameter. Right. The first guy's diameter was half of the whole thing. The second guy's was 1/4 of the original, and so on and so forth. Okay. Let me sort of sketch out the idea. Maybe I'll write it more carefully next time. But now, if we take the intersection of all the I sub n's, right, from what we just said, that contains some point. Right? It's nonempty. So contains some point, which we'll call x star. Okay. Okay. So far so good? Right. The intersection is non-empty, and so it contains some x star. Now further, x star is contained in some G alpha naught, right? We have the cover of all of I. X star lies inside of that, so it must lie in one of these guys. Okay, right? So here's X star, right? X star is somewhere down the rabbit hole, right? In the intersection of all these guys. Okay, so that's X star there, but we know that there's some G alpha that covers it, right? There's some G alpha that covers X star. So here's my X star, there's some G alpha covering it, right? G alpha is open, right? X star is interior to G alpha, right? So so X star must be contained in some ball of radius r around it that's contained in the G alpha. Right? We know that the G alphas were open, so we know that X star is interior. Okay, but, and here's the contradiction, but now choose n small enough, choose n large enough that 2 to the minus n delta is smaller than r. Okay, so we know that this guy lies in the intersection of all those little rectangles. Well, choose one, go far down enough that the diameter of the rectangle is smaller than the radius of the circle, smaller than the radius of the ball. But then I sub n is contained inside of G alpha. I sub n is contained inside of G alpha, but we said that the I sub n's could not be covered by any finite subcover, but we've just covered it with one set. That's certainly a finite subcover contradiction. That's the idea. Sorry, I've kept you over. I'll try and sketch this out again at the beginning next time. But yeah, you do this zooming in, you get the point, and you get the contradiction. Okay, see you next time.
Thank you.
Are you welcome? See you. Bye-bye.